I'm going to try to show why this equation should be expressed in a very linear, in a very symmetric form. Okay, the first thing I'm going to do is I'm just writing it out on the paper the way he had it. Okay. Second thing, I'm going to expand it. So this t prime is gamma t minus v, I don't know what order to put in things in, x, v gamma x over c squared. I'm going to reverse this one. Probably should have, yeah, I'm going to reverse this one. So it'll be gamma minus gamma vt. So we got the t's in the same order. And plus gamma x. Okay, good so far, right? Now, the first equation, t prime, I'm going to multiply it all by c. So I'm going to take this part and multiply it by c. So it's going to be c t prime equals gamma ct minus v gamma x over c. Good. Okay, and this one I'm going to multiply by c over c. So it's going to be pretty much essentially the same, except it's going to be gamma v over c ct minus. So you see I multiplied this by c over c. And then this is plus gamma x. All right, so now what I'm going to do is turn this into a matrix, or well, actually, yeah, I'm going to turn it into a matrix multiplication. So I've got a CT over here and an X down here. Okay, so now what I can put in there is up here gamma and minus V over C gamma, and I'm just going to call this V over C beta. It's going to be your velocity as a proportion of the speed of light, minus beta gamma, and then that's multiplied by x. And then x prime is going to be negative beta gamma, because it's v over c times gamma, and then that's multiplied by your ct, and then gamma over here. And you see how symmetrical that is? Ct prime x prime is equal to gamma, negative beta gamma, xctx, negative beta gamma, gamma. It's just diagonally the same here, diagonally the same there. And all you had to do was kind of change this to a ct prime instead of a ct. Now, this form to me seems much more easy to remember than this form. Now, maybe you don't like it because you actually have to do a little bit of work to figure things out, but ct prime equals gamma ct minus beta gamma x. That's our equation for time. And so t prime is equal to gamma t minus beta gamma x over c, which is equal to gamma t minus, we'll just go ahead and change that to a v over c squared gamma x. Okay. So in the paper that I'm looking at, which is called the Lorentz transformations at low speeds do not reduce to the Galilean transformation. Essentially what Stefano Quattrini says is that this part of the equation reduces to the Galilean transformation. He does so by looking at x prime equals negative beta gamma CET plus gamma x, and finding that when he plugs in gamma equals 1, which is his way of saying we are at low speeds, that beta gamma CT goes to VT minus VT plus X, and boom, voila, the X prime part reduces to the Lorentz transformations. However, he points out that T prime, which I did already, T prime, when you reduce gamma to 1, it comes out to be T minus Vx over c squared. The gamma, setting gamma equals 1 does not make this cancel out. So, and indeed he's right. For this to come out to be close to 0, you need two assumptions. V over c is much, much less than this, much less than 1. And you also need x over c is much, much less than 1. Actually, you don't need it much, much less than 1. You just need it not too big. Because if this is much, much less than 1, and this is huge, then you end up with sort of a significant number there. For instance, the orbital speed of Earth around the Sun is 30 kilometers per second, which is a delta V, when we go all the way around the Sun, of 2 times 10 to the negative fourth kilometer c, 2 times 10 to the negative fourth c, or delta V over delta c, or rather delta V over c of 2 times 10 to the negative fourth. Meanwhile, if you look at the Andromeda galaxy, which is 2.5 times 10 to the sixth light years away, divided by 1L, light years cancels out with light, and you get 2.5 times 10 to the sixth. You multiply these two numbers together, and what you get is that an event that is occurring now at Andromeda Galaxy is swinging forward and backward in time by about 500 years each time that Earth cycles around the Sun. So if you look at a space-time diagram representing that, you've got events over here, like where Andromeda Galaxy is, swinging back and forth of 500. It's very small on this scale because this is 500,000 light years, and this is just 500 years. But you have this swinging back and forth of events, these events that are simultaneous with this event. So that's not what the Galilean transformation does. The other thing that what essentially the Lorentz transformation does is when that swings forward in time, events over here will swing that way, events over here will swing this way, and that goes up on that way, and then coming down this way it stretches the opposite direction, and you get this curving over here that way. So this is kind of what the Lorentz transformation does. It moves events on hyperbolas in along these different paths. And essentially the Galilean transformation, it flattens all of this into, it flattens that to a flat surface, and you get the just straight lines of the event staying in the same time, but moving forward and backward in space, or left or right. So the question of whether the Lorentz transformations, which go like that, reduce to the Galilean transformations, which go like that, kind of depends on how important it is to you that these events over here are swinging up and down. In general, that's not going to have any real effect on us, but you might find it important, and so if you do, then you could legitimately say, hey, people, it kind of depends on what somebody means by the Lorentz transformations reduced to the Galilean transformations, because some people might say that and have the correct concept in mind, and some people might think that this phenomenon disappears altogether, and they would be wrong. Under the Lorentz transformations, these events do definitely move forward and backward in time. However, we will never see any of that motion, the forward and backward motion in time of those events. We can only see these events that are coming up at us this way, and these events which are coming up at us this way. Only those events that are coming at us from those angles are going to be seen. And so we don't actually observe these events moving forward and backward in time. That's not to say these don't move forward and backward in time. They do. This direction is towards the past, and this direction is towards the future. That direction is further away, and this direction is closer. And they will move along that path and that path, depending on whether we accelerate towards them. When we accelerate towards them, they will move further away and further into the past. And when we accelerate away from them, they move closer to us and less far into the past. Now, I should say, I'm going to make the point that I am talking about the Lorentz transformations right now. And another thing that Mr. Quattrini has been talking about is the Tangerlini transformations. And essentially, the way I would describe the Tangerlini transformations is that they basically do the Lorentz transformation first, and after these events have moved up a little bit and these events have moved down a little bit, then they do what I call a position preserving temporal skew, which is where they just move this back up to where it was, and they move this event down a little bit, so they even them out again. And mathematically, what that would look like is you've got your Lorentz transformation here, which is gamma, negative beta gamma, negative beta gamma, and gamma. And you got, what do I have? X and CT. Actually doesn't, I put them in the opposite order earlier, but so that's, I'm going to put another matrix in here. Sorry, I should have used pencil. Okay, but the other matrix is 1, 1. It doesn't, and beta, 0. And essentially what that beta does, look what it does on the bottom. Beta times gamma minus beta gamma is 0. and then beta times minus beta gamma is minus beta squared gamma, minus beta squared gamma plus gamma. So xct, this is going to be our t, we'll call it t double prime for since t prime was the Lorentz t, and t double prime will be the, what do we call it? Tangerlini t. So beta squared gamma plus gamma is, well, replace gamma with 1 over square root of 1 minus beta squared, and you can see that this is 1 minus beta squared over square root of 1 minus beta squared, which is 1 minus, it's just square root of 1 minus beta squared, which is 1 over gamma. So the Tangerlini t is just, or the coordinate transformation, the whole coordinate transformation, it has the exact same form for the x double prime and the x prime, gamma x times negative beta gamma t, but then it changed the t double prime so that you've got 0 and 1 over gamma t. And what happens in the Tangerlini transformation? Well, imagine that you have something, some light bouncing back and forth between two mirrors, and one is at 0, 10, 20, 30, 40, and then we speed those two, we like look at those from another perspective, and we all agree, I'm going to keep the speed of light constant, like this. So now this reads 0, this reads 10, this reads 20, this reads 30, this reads 40, and 50. I didn't write down 50 on this one, but 50. So, but you can see this little problem here that, hey, that is not, this is not halfway between here and here. So what the Tangerlini transformation does is, well, before I do that, let's come back over here and say 10, 30, 40, and what we got, 20. We're just going to assume that those are synchronized, right? Okay, and over here, those would be marked halfway between 0 and 20 is 10, halfway between 20 and 40 is 30, and halfway between 10 and 30 is 20, and halfway between 30 and 50 is 40. So the lines of simultaneity, if the speed of light was preserved, should be slanted a little bit from that to that to that to that. So the unprimed, the original lines of simultaneity were slanted by changing the speed of light. So what the Tangerlini transformation does is it fixes that. It says, no, we're going to move this up a little bit and this down a little bit, and make this go up a little bit and this go down a little bit, and this go up a little bit and this go down a little bit, and that go up a little bit and that go down a little bit. And what this does is it makes absolutely no changes in any of the observational effects, but it changed the speed of light in the two directions, and it basically what I would call a position preserving temporal skew. It's very similar to the Galilean transformation, but is not associated with a change in velocity of the observer. So it's just kind of an arbitrary fix, and really if we were honest about it, we shouldn't actually assume that our original that that this was this first thing was in the correct universal stationary uh, reference frame. We would want to assume that we don't have any idea what that is. We don't have any idea what the actual correct reference frame is, so we'd actually put a value here to represent that unknown, that known unknown, that we have some relative velocity with the true stationary of the universe. And so this would be some constant, or well, it wouldn't be a constant. It would depend on our relative. It would just be related to our relative velocity with the true stopped. And and if there is some real true stopped way of knowing what that speed is, I don't think there's any observational way to detect that. It's just kind of a way of adopting a Ptolemaic or Aristotelian concept of relativity, uh, even though we've got this Einsteinian or Galilean concept of relativity with the Lorentz transformations as they are.